You are given a value n to generate an imaginary n by n chessboard. Return all distinct ways to place n queens on the chessboard such that no two queens can attack each other. Hi everyone, we're here today for another Exponent mock interview with Jared. For those of you who aren't already familiar with Exponent, Exponent helps you get your dream tech career with our online courses, expert coaching, peer-to-peer mock interviewing platform, and interview question database. Check it out at tryexponent.com. Okay, thank you so much for being here with us today, Jared. Would you quickly introduce yourself for our viewers?
Hi, yes, of course. Hi, happy to be here. Yeah, my name is Jared. Right now, I'm a software engineer. My past experience includes, doing software engineering for companies like Google, Airbnb, NVIDIA, and that's all after kind of graduating from the University of California, Berkeley, where I got my degree in computer science.
Awesome. Yeah, it sounds like you have a lot of really interesting experience. Okay, so let's get right into our question for today. The question is, you are given a value n to generate an imaginary n by n chessboard. Return all distinct ways to place n queens on the chessboard such that no two queens can attack each other. And for reference, queens can move vertically, horizontally, and diagonally.
Okay, awesome. Just to kind of reiterate the question to make sure I understand it properly. So we're given like a set value n to generate an n by n like width and height chessboard. We're only working with multiple of a single piece that's a queen that moves basically any number of steps vertically, horizontally, or diagonally. And we want to make a sort of configuration on the board such that they can't attack each other. Does that make sense?
Yes, exactly.
Okay, got it. Yeah, a few clarifying questions, I guess. So I guess the first one is like, how should our data like be represented, like in terms of like a return value? Does it matter, or are you looking for a specific format?
So you can format it, the output, as a list of strings where in each string, a Q indicates that there's a queen placed there, or a dot indicates that it's an empty square.
Okay, awesome. Sorry, I'm just taking some notes here. So a Q equals there's a queen placement. And then the actual, like, I guess, dot value or the period means that there's like sort of an empty space.
Yeah. Let's share your screen.
Okay, awesome. Let me do that once. Okay, great. Yeah, does this work?
Yes.
Okay, sounds good. So yeah, we're working with, again, Q, it means a queen placement, and we're going for like a list of strings to represent the board. So I guess just writing an example to make sure I understand it properly. So for like one example would be like, if we're working with like a, let's say a 3x3, one can be like dot Q dot. We can also have a, this will be one row. Oops. This can be like a second row, not necessarily a valid board by any means, but this is just kind of one example of like a type of board that we might want to, represent our data of as we kind of continue forward. Okay, and I think we already covered like what kind of directions queens can travel. So just to kind of note that here, they can travel horizontally, vertically, and diagonally, and like this is like any number of spaces, I believe. And is there a like requirement? So like how many queens like do we have to place? I believe it was like n number, like so like if it's a 9x9, we want to place 9 queens. Does that work?
Yeah, exactly.
Okay. And what are the constraints of this board? It would really help in terms of evaluating the actual like runtime when it comes to the type of data that we get.
Yeah, so you can assume that n will range anywhere from 1 to 9.
Okay, so n is like one to a value of 9. Okay. Okay, awesome. So yeah, in terms of, I guess, thinking about this logically, there are a few approaches that kind of come to mind. The first one, which is probably more of a brute force approach, is kind of placing queens at, deciding whether or not to put a queen at a particular space, doing the same throughout the entire board, and then kind of evaluating at the end whether or not the board is like a valid board such that no queens can attack each other. This is probably a non sort of optimal solution. We're looking at very like exponential runtime. So I'm definitely going to, I think, reconsider this approach and kind of go toward more of, leveraging some of the information that we do have to kind of to play to our advantage so that we're able to do this a lot quicker. So thinking about the overall algorithm, a few things that kind of come to mind is one, since queens can go entirely like horizontally, one of the things that comes to mind is like being able to kind of build the board at each individual step, and then seeing and evaluating whether or not a queen can be placed at a particular position. So one thing that kind of comes to mind is if we have our, we're creating our overall like answer set, and we are able to append the first row by itself, and then gradually append every single subsequent row with a queen in place. Because we need n different queens, one of the things also we know is that no queen can probably be on the same row as another queen. So I'm expecting that every single row should have one queen on them. So each row should have exactly one queen. That way they're not positioned so that they can attack each other. And then from there, we have a main decision to decide where does this queen go in a particular row. And one of the points of validation that we have to make, since we already know there's one that's going to be on the horizontal level, is we need to verify this both vertically with previous rows, and also diagonally, again, against like previous rows.
Yes.
So that's kind of the approach I'm going to do, build the board kind of step by step. And then once we have n rows, we can evaluate at that point whether or not it is sufficient enough to, output as a response value.
Okay, so to clarify, when you say that you're building the board row by row, does that mean that for each successive like square that you populate, you're already reducing the number of possibilities of what that space could contain, because you know that from these constraints that you know that like there's only one queen per row and so on?
Exactly. So there's one queen per row. So we know that we do have to place one at every single, you could think of iteration. And then from there, whether or not we continue is going to be completely dependent on whether or not that queen placement is valid compared to the previous rows. And then if we ever get to a step that we're at row 9 or up to 9, whatever n the value of n is, then we can return that as this is an optional valid board.
Okay, great. So it sounds like you're essentially pruning the output space as you're creating the output.
Exactly. And then once we kind of get to a solution, and then we've consistently validated it at every single row appending, then we can kind of put that as one of our response values.
Okay, great.
Okay, awesome. Yeah, I guess just to kind of start on a like solution, one of the things we can do is like, count, let's see, we'll call it n queens for now. And we know we're given a value n. And again, this n can basically be anywhere from like 1 to, again, to 9. So one of the things that we need to do, of course, is, how are we going to be appending every single row? The way that I think is the easiest way of doing this is to kind of have this within a recursive function, so that at every single step, we're able to, append based on, what the previous state of the board is. So one of the things that we'll do is we can actually do something like a DFS or like a recursive function to actually append at the state of the board. So one of the things that we'll also need to do is like, let's figure out what our output value is. This output value is going to be basically a list of, valid board states. And then what we'll do is we'll actually perform a DFS or like a recursive function on the board that we are creating. So again, the board is going to be, as mentioned before, a list of strings that represents the current state. And then at the end, what we'll do is we want to return like the output that we're going to constantly be appending. And when we actually want to start this board, what we'll do is we will actually start with a recursive function on performing our DFS based on a few things. So one is going to be, how many rows have we kind of gathered so far? So the first one we need is some sort of indicator. We'll call it I, to basically include, hey, what state of the board are we, or what row of the board are we trying to append at? And we can start this at 0 because we're going to be building up from 0 rows. And the second one is going to be the board state, which at the initialized state is going to basically be an empty list. And we're going to keep appending strings to this list as well. So the first thing we need when we're actually doing this recursion is sort of implementing our sort of base case. So what happens when we have gotten to, we have built our n by n board? What should we do at this case? So that is going to be when I is going to be equal to n, i.e. like the n that was sort of passed into n queens here. So what we can do is, if our I value is equal to the value of n, then what we want to do is we actually want to perform like our output dot append the current state of the board. So the board that we have up to this point have validated at every single incremental step.
Okay.
The next thing that we'll want to do is, hey, let's assume that we're not at the sort of, final part of the board. So let's say that we are in sort of that half step. We are building our board row by row. One of the things that we'll want to do is kind of figure out at what point, at what sort of position we want to place that queen. So we've already validated that we need to add a queen at each row appending. So what we'll do is we actually need to iterate through every single column and evaluate whether or not this is a valid placement for a queen at this column. So what we can do is we can do for every single column in range, and we know we're going to have n different columns as we build up our board. We need to evaluate, hey, if we'll call it like, is valid placement of a board at a particular column. So what this is going to do, we'll create a helper function for this a bit later. This is going to determine, hey, can we place a queen at the most recent row, or we can think of it like the bottom row of the current board at column call in this case. And then if it is a valid statement, then what we want to do is we can actually append this row to the board itself. So one of the things we'll want to do is we'll actually want to create a copy of our board. We do copy dot, deep copy of our board. And then we want to actually add our copy board dot append. And this is going to be the column that we've decided to place it at. So assuming that we have identified a column that we're able to place the queen, we need to basically append the string that represents that particular row. And we already know what column we're placing it at. So actually one of the things we can do is we can use a period to represent basically the empty states times the column that we're at, plus the value that we're going for Q. So this is going to be, we're placing it at column Q. And then plus, again, we want the empty spaces all the way until the end, which is basically, n, which is the number of total columns minus the column that we choose. And then we're also going to be doing a -1 to represent at this point, we did a -1 because we have already taken up one of the spaces with our queen. And then from here, we want to run our DFS on our new board, which is going to be I+1, representing we are at one more column lower with our copy board down here. Mm-hmm. So I like the format of this, wanted to kind of take a moment to kind of see whether or not this kind of makes sense. Otherwise, the next step in the sort of process is kind of outline, what does this validation look like?
Yeah, makes sense to me. I'd love to see how you're validating it.
Yeah, awesome. So let's start off by creating, let's actually define what it means to validate at a particular board state. So again, one of the things we need our actual, the board that we are going to be validating and the column that we intend to place the queen at the most recent row that we are appending. And the way we can do that is a few things. So based on our initial assumptions, one, we want to verify, that the queen follows the same rule, that there's not two queens on the same row. And we already do this because we only append one queen per row. So we don't have to worry about that condition. The next one we need to do is, verify against the queens that exist above it. So we want to make sure that there are no queens that exist vertically from position, column. Yeah, from the actual column that we are planning to append to. And the way we could do that is we can go, for a row in, what we want to do is we want to iterate through the current range of the board for range and current length of board. If the board at index, so we know which row we intend to place it at, so we're verifying at every single row, and we also know what column we want to place it at. We want to make sure if there is a queen that exists at this particular array index, then what we'll do is we want to return false. So that helps us complete the step. Hey, do we verify vertically for this particular column that we want to append the queen at? The next one that's a little bit more challenging is verify diagonally. So one of the things that we'll want to do is make sure that, hey, if we plan on placing the queen at this particular column, how do we make sure that every row above it, there's not another queen that exists at a diagonal from this particular index? So, and also this is also from the left diagonal and the right diagonal. So the way we can do this is we also want to iterate in a very similar fashion to kind of how we did above by going row by row. But we also need a indicator that represents how far left or how far right should we move depending on the row that we're looking at. So what we can do is we can add a variable, we'll call it deviation. How much does this deviate from our current column index? Because we are working right now with we can iterate backwards. So we can sort of start this deviation at 1, meaning that when we check the row above the one that we're currently at, let's go 1 space to the right and then also 1 space to the left. And then to actually iterate through this, we can go for every single row, and we're going to be widening our scope as we traverse up the matrix. So what we'll do is for every single row in range, we'll iterate through the length of our board -1, and we will continue decrementing from the bottom row. So we'll evaluate the most bottom one, left and right, and then we'll go up a level, go 1 more space over for both the right and left. And then what we'll do is if the board at index row and then at index column that we choose, but the column is going to be plus the deviation. If this is equal to Q, then what we'll also want to do is return false, meaning that there is a Q that exists at this particular level. And then very similarly, we will also want to check the left side. So we'll also want to subtract the deviation at each particular step. Now, one of the things that kind of stands out in this current situation is, hey, what happens if we're evaluating on a very right queen, and then we have the opportunity to get sort of an index error over here? What if we go too much to the right or too much to the left? So one of the things that we'll want to do is if the column plus the deviation, in this case, we are checking on the sort of right side. So if we want to check that this is less than the length of our board at index row. What this means is we want to make sure that we are not going to go get an index out of bounds error. We want to check, hey, if it's in the bounds of the board and it's a queen. Because if we are out of bounds of the board, then that's totally fine. There's not a queen, further than it that can sort of attack it. And we'll want to also introduce the exact same format here. However, since we are going to the left, we want to make sure that this is greater than or equal to 0. Mm-hmm. And this is going to be column minus the deviation.
Okay.
Yeah, so that's kind of how we're going to be evaluating if there's a queen exists. And then otherwise, we're going to return true.
Great.
Yeah.
Okay.
Yeah, I guess one other thing that kind of stands out to me, just kind of looking back at doing a thorough overview on kind of how I've kind of added this implementation is one of the parts that might be a little less optimal is the actual deep copy of the board. The reason why we do that is so that we're not confusing pointers. We're not, we're working with an isolated copy of the board. But one of the things that we can add sort of as an optimization is to actually you do some backtracking and actually only copy the board at a particular moment. And in this case, we only need to copy it when we actually append to the output.
Right.
And then also one thing that we can add is if we just kind of add on to a singular view of this particular board, do the recursive function on this singular object. And then afterwards, we can actually add some backtracking over here to basically pop the last item off the board. That way we only maintain one singular state until we need to actually copy. So one kind of optimization that we can kind of add there.
Okay, yeah, that makes a lot of sense. So I'd love to see you test your code on a few test cases then.
Yeah. So let's kind of talk through a few of the potential solutions. So one, we know that, let's work with like the single case one. So what happens if we have like a 1x1 square? So we would kind of assume that this would work for like a single queen. And then what we can do is we can actually print out the output for, let's say, oops, sorry, not output. We'll actually want to print the n queens for, let's say, an n by n board. So what we can do is we can kind of talk through what we would expect, and then kind of see if that kind of matches what we were expecting. So if we actually print the n queens for number one, we can kind of run our code here. Oh, sorry. It looks like we were getting a string object not callable. 1 second.
It needs an asterisk. The multiply needs to be after the dot, the second dot.
Oh, you're right. Thank you so much for that. There we go. So we can kind of run through this. And yeah, as you see here, there's one valid state that we would expect. There's not two queens that can attack each other from a particular state. What we can do is now we can kind of move on to a 2x2. And right here, you'll kind of see a empty list. And the reason why we'll see that is because there's no real configuration for a chessboard such that we can have two. So kind of talking through how that would work, if we needed two particular queens, if we did have a queue on our top row and our bottom row, a queen does not fit because we can either attack each other diagonally in a case like this, or if they were stacked on top of each other, then they would also be able to attack each other there. So yeah, that particular one doesn't work. We can do 3, move on from there. Also very similar. I won't go too much into the approach because it's going to be a very similar situation as the first one. But we can go on to a value of 4. And here we kind of would expect, let's see. Sorry, 1 second. Call on board. Let's see. Copy board, copy.deep copy of the board. Now it's time for the debugging portion. Let's see. It looks like we do get a copy. Let's see whether or not we are actually printing the board here. Looks like we are not. If I is equal to n, that means that we're not getting into this case. However, we iterate through every single column n, and one of the things that we have is if I is equal to n, we append the board. I think that this else statement is kind of confusing it because we want to continue tracking every single one here. Is valid placement, and the board, n times column. The board in this case. Let's see how much we grow the board. And this is in a value of 4. Oh, I see. One of the things that we didn't do here is we just didn't do deviation plus equal to 1. We didn't increment the deviation at every single point because we want to keep branching it out. There we go. Yeah. Okay, perfect. So in this case, what we'll do, very similar to kind of how we did before, if we have, 2, again, not a valid placement. If we kind of move on to 3, we can see, again, for the similar fact that 2 doesn't work, that it doesn't work in the 3 case as well. But once we kind of move to 4, we actually kind of increasingly increase our number of options that we're able to kind of populate. So in this case, it's a little bit hard to read, but actually, let me remove this print statement here. but we get two different states of the board, one being here and then one being here, such that in both states, there's not a queen that can attack each other from every single part.
Okay, great, perfect. I think this is a great place for us to pause. Congrats on finishing the interview. That was awesome.
You're awesome. Thank you so much.
Yeah. Okay, so I'd love to do a quick analysis of that. So what did you think of this interview? What do you think went well? And what do you think you would want to improve on?
Yeah, so one of the things I think went well is just being able to, I think, iron out the algorithm kind of beforehand. I think it's very helpful to kind of, talk through my approach kind of verbally before kind of diving in. That way I have a, better understanding of whether or not the algorithm would work or my approach would work initially, because I think at various points, the interviewer can kind of point out different states that, might need a second look, and also can guide you on the right track if any, I guess, gaps are made. So I think that was a, good part of it. In terms of points of improvement, I think, kind of making sure that all like edge cases are handled. Also making sure to kind of look back on code to kind of make sure that it kind of fits the algorithm I've kind of applied is something that, yeah, I think I'm always seeking to improve.
Yeah, awesome. I agree with a lot of those points, actually. You, in particular, did a really great job of talking through your thoughts as you were writing code. So it was really easy to follow along with your logic and understand what each line of code did, which is great. Yeah, and I also really like that you managed to improve from the brute force solution to this recursive backtracking solution, which, because you're checking for the validity of the board as you're generating the boards and not generating any invalid ones, that saves a lot on runtime and space complexity too. And then as for things that would have made this even better, so I'm curious what you think about so the validity check. Is there a way to reduce the runtime of that, do you think? Because right now you have to check every single row, every single column, and every diagonal to see if there's already a queen.
Yeah. So that's actually one thing that I think, given more time, I think is a very easy place to kind of improve the runtime checks. And that's a great point. I think one of the things that if there does exist one of the things that we do here in this solution, as you pointed out, is we actually check every single point like diagonally and also vertically as well. So one of the things that we don't necessarily need to do is like, hey, if there is a, if there's a way that we can sort of pass down as in every single row, whether or not that particular diagonal is free, is something that way we don't have to necessarily go back and check every single row in between. A big reason why I decided to, felt comfortable with this approach is also because of the sort of constraints that we were given, that n can't be, from 1 to 9. Because of that, we're looking at like sort of a constant space. We're only checking, at most 9 different rows. So yeah, I do think that that's definitely one point of optimization. And that's one, I guess that's the reason why I felt a little bit more comfortable having a little bit more of a naive approach in that sense.
Yeah, okay, makes sense. And then for larger values of n, it probably would make sense to do that, to pass down that bit of storage that tells you which rows and columns and diagonals are already populated, right?
Exactly. Something more like a dynamic programming approach where we're able to, check all the previous rows based on, one kind of check for at maybe the most recently updated row.
Mm-hmm. Okay, perfect. Thank you so much for joining us today, Jared. I think we learned a lot from you, and this is a great interview. Okay, and thanks everybody for watching, and good luck on your upcoming interviews. Bye all.
Thanks so much for watching. Don't forget to hit the like and subscribe buttons below to let us know that this video was valuable for you. And of course, check out hundreds more videos just like this at tryexponent.com. Thanks for watching and good luck on your upcoming interview.